there's this event in Thessaloniki going on now. This what is it called in English?
I don't know. It's like an international meeting exhibition for business.
They do once a
to
year.
meet up and
Prime Minister go and very cool. Minister seems like that.
Event mostly.
So some people have gone there.
Okay.
Some people missing. Some are on the mountain. And that is the push.
No.
Can I meet people? I'm going to just join in live. Going to come in. For people to come. I hope my other students will come. I go. I'm just calling. Our internet is a bit
unstable.
a couple more people are.
Yeah, whenever you say.
Yeah, so I wish I had come a couple of times.
Yeah?
Yeah, because he was thinking of deep spec, putting it on my list or something like that, and then COVID happened and we stopped, well, everything froze for a while, and then we started it up again. We applied for funding for spectrograph. Unfortunately, we got the answer at the end of July that we didn't get it, but it's a very competitive year.
Yeah.
5%.
Oh, wow.
Success rate is worse than the RC. So we're exploring options now here. We don't know if we were trying to get the telescope to do transient science because it's not doing much science, and it's a shame.
Where is it?
In the Peloponnese, it's 2-3 hours from here. It's a dark site. Weather is what, 40% wind, something like that. Okay. And should I start? There's no 4 people for sure coming.
I'm no rush. But anyway, it's we'll start at 10 past.
Okay. Here at the universities that they do that, I think a quarter past. Here we try to keep it on time. We have 5 minutes to go and get the people. Okay, thank you everyone for coming. It's a pleasure today to have Dr. Iair Arcavi with us here today from Tel Aviv University. in Israel. He was actually here for a conference last week in Crete, and he accepted the invitation to stay a bit longer and come give a seminar. So a few words about him. He got his PhD in 2013 from Weizmann Institute in Israel. After that, he went to California to Las Cumbres Observatory for a postdoc, and then was an Einstein Fellow from 2016 to 2018 in Santa Barbara. And after that, he returned to Tel Aviv University, where he's working now, and also has an ERC starting grant, from what I understand. So, and he'll tell us today about stars disrupted, destroyed, and coalesced. So a bit for everyone.
Yes, thank you. So yeah, thank you very much, and thanks for the invitation. It's great to visit. So yeah, this will be a bit several topics of what we're working on in my research group. So if you find one topic not interesting, don't worry, because in a few minutes it will switch to another topic. Okay, this is a picture of the Black Gem Telescope Array in Asiya. I took this a week and a half ago. I came from there before the conference, and this is one of the facilities that we started using, but I really like it because there are 3 telescopes, and also this talk is about 3 main topics that we study in our group, which is basically all the violent ways that stars can die, either disrupted by a black hole in a tidal disruption event, through exploding through a core collapse supernova, or merging in a coalescence, compact binary merger. So the reason we study these things is because they can teach us a lot of different astrophysics. Okay, so let's get started. So the first one I want to talk about is tidal disruption events. So this story starts about actually 10 years ago, this year, where we discovered a new class of transients in galaxy centers. These were all in the optical and UV, more luminous than typical supernovae. And their spectra looked like nothing we had seen before in supernovae. They were very blue. Here you see the luminosity. This is now 10 years later, so it's quite varied. And in the spectra, you see that some of them have a broad H alpha, and some of them have, all of them almost have this very broad and complex feature around helium-2, which we had never seen in supernovae. They all happen in the centers of non-star forming galaxies. So the interpretation was that these are tidal disruption events. Stars that get very close to a supermassive black hole. So if they reach a distance equal to this tidal radius, this is where the forces from the black hole are stronger than the self-binding gravity of the star. Beyond this radius, the star will get disrupted. It will no longer be self-bound. And then this was predicted, okay, so it's one of the few things in astronomy that was predicted before it was observed, in 1988 by Martin Rees. Half of the star will get ejected, and half of the star will be bound to the black hole and somehow eventually accrete, and then you should get a flare of radiation. These events are very rare, about 10 to the minus 4, 10 to the minus 5 per galaxy per year. This is about 1% of the supernova rate, roughly. And the idea was that they will form an accretion disk, and accretion disk can emit in the X-ray, so we should look for flares in the X-ray. Okay, so in order for this to happen, you need the star to be, the pericenter of its orbit needs to be within this tidal radius. It needs to be put in this kind of orbit. This is parameterized by this beta. It's just the ratio of the tidal radius to the pericenter. You want it to be greater than 1, right? You want the pericenter to be inside the tidal radius, otherwise you don't get a disruption. And then the other important scale here in this problem is the gravitational radius. You want this to be outside the gravitational radius, because then the disruption will happen where you can't see anything. Okay, so for you to see something, it has to happen in between these 2 radii, and for it to be greater than for the tidal radius to be outside of the gravitational radius, the mass of the black hole needs to be less than 10 to the 8 if you're disrupting a solar mass star. Okay, so remember this number, this will be important later. Massive black holes above 10 to the 8 solar masses, we don't expect to see anything, because it will all happen inside the Schwarzschild radius. Okay, so this was the picture from Martin Rees in 1988. Half of the star is ejected, half of the star comes back. This is the tidal radius. This is a more modern numerical simulation from 2013, and this is one of the latest numerical simulations from this year. So you see already the inherent problem in simulating these events, that you have many, many different scales. You have interesting things happening on small scales near the black hole, and the star is stretched. Okay, this is the star, this is the black hole. The star is stretched by tidal forces to very large scales. So it's a very difficult numerical problem to solve. Okay, and then the question is, okay, but what will we see? So the first idea was the material comes back, so this is the half of the material that's escaping, half is coming back, it's forming an accretion disk, we should see some accretion emission, which is typically in the X-rays, okay? But that is exactly not what we saw 10 years ago. The new class of transients I told you about, they were all in the centers of galaxies. The luminosity declined at least power law into the minus 5/3, which is expected from the rate it takes mass to return to the black hole. This is just from Kepler's law. But from an accretion disk, we expect these temperatures, the observed temperatures in the optical and UV, much lower. The tidal radius is typically 10 to the 13 centimeters. The radius we saw, black body radius of this emission is 2 orders of magnitude larger. And even if you say, okay, we don't understand exactly the emission, the total energy, right, should be okay. And this is the total energy you expect if you throw a solar mass star at a black hole. And the typical energies we see are 2 orders of magnitude less than that. Accretion disk should have an evolving temperature, we see constant temperature, and I showed you some cases where there was no hydrogen in the spectra. This is very strange. How could you hide the hydrogen if you disrupt a star, if it's a typical star? So none of this fits what we expected to see from a tidal disruption event. So this is the big puzzle today in the field. Why do tidal disruption events emit optical and UV light? I should say we also see events that emit X-ray as expected. But this new class we discovered 10 years ago, which is only growing, the big debate till today is how come we get the emission in the optical and UV and not as expected. Okay, so your first thought is these are not tidal disruption events. Okay, so we'll get to that in a second. But assuming that they are, people started to try and explain what's going on. So the first solution that proposed is, okay, you form an accretion disk, but it's not in a vacuum, it's surrounded by some reprocessing material, either that was there before or that's part of the star that's been disrupted. And as the X-rays come out, they pass through this material and they get reprocessed into optical and UV. And this explains how you get the lower temperatures, the higher radii, because the photosphere is actually not in the accretion disk, but it's in this reprocessing material. And these are models that show you also if you change the radius of the reprocessing material, you can turn on and off the hydrogen without touching the helium, which is exactly what we see in observations. Basically, if the reprocessing material is too confined, small radius, the temperature is too high, hydrogen is ionized, you won't see it in the spectrum. And if you let the radius be larger, here you have some neutral hydrogen that you will see in the spectrum. So you expect to see the hydrogen where the blackbody radius is larger, and this is exactly 8 years later after this model, we now have enough events to show this is the blackbody radius and this is the luminosity in hydrogen, and it is indeed roughly correlated. So when you have a larger processing envelope, you have some neutral hydrogen and you see the emission lines, and if it's small, you don't see the emission lines because it's mostly ionized. So this is a great explanation. A next step was even to say, okay, if this reprocessing material is not spherically symmetric, you will have a viewing angle dependence. If you look through here, you will see these optical events that we see. If you look from here, you will see directly into the accretion disk and you will see the X-ray events that we see as well. So this was kind of a unifying picture, okay? So supposedly problem solved, except when you do the simulations, the numerical simulations, the more modern ones, here is a star being disrupted by a black hole. There it was disrupted. Now half of the material of the star is escaping, is unbound, and this is the half of the bound material. It comes back. The traditional picture was, okay, it will get squeezed here in pericenter. You form this thing called the nozzle shock at pericenter. This dissipates energy, and then it should, to circularize and form an accretion disk, you need to dissipate energy. But when you do the numerical simulations, it doesn't dissipate enough energy. Instead, the material comes back, and because of precession, GR precession, it hits the incoming stream and forms a shock out here at apocenter. This is known as the outer shock. And this will dissipate energy in order to circularize and form an accretion disk. Okay, but these outer shocks, when you do the calculation of what's happening here, actually dissipate energy in the form of radiation that looks exactly like the radiation we see. The temperatures, the radii, and this also explains how you dissipate the energy to form the accretion disk maybe months, years, or decades later, depends on the system. So this picture actually says you're not seeing the accretion disk being reprocessed, we're seeing what happens before the accretion disk is formed, which is up here in these outer shocks, and that dissipates the energy, and that's what you're seeing. Now it's really important we know what we're seeing because we want to use this radiation to infer the properties of the black hole. right? And if the emission is coming from here or from here, it's a very different model. New simulations from this year actually go back and say, actually, so this is the star being disrupted. These are really state-of-the-art numerical simulations. This is time going down, and here you're seeing the density of the material, and here you're seeing where there is energy dissipation. So this simulation shows that you actually do dissipate energy in the nozzle shock. Not enough to completely circularize, but it's enough to start the circularization process, and you get shocks between the material and the stream. So initially we thought the shocks were out here. This model is saying the shocks are further inward, and you do kind of get both energy dissipation from here and energy dissipation later from the accretion piece. So this means you might see a flash of radiation during this part of the event, and then you will see the main radiation here. And this was actually seen, okay, so this is a year before this, but the model was predicted this before this was published, where we see this is the main optical UV event, but at the beginning there's this one X-ray flare before the main event from E Rosita. So this would have been impossible to detect before E Rosita, where we see this X-ray flare, which could be attributed to this energy dissipation here in the nozzle shock, and then the rest is from the formation of the accretion disk. So we now not have one explanation for the emission, we have four. The initial explanation, you should just see the accretion disk, okay? And then the new explanation, it's reprocessed, it's the accretion disk just reprocessed, it's these outer shocks, or it's this intermediate solution where you have some radiation from here and some from the collision which happens further in. Okay, so this is now the main debate in the TD, tidal disruption event field. What is causing the radiation that we see? Because we want to use this radiation, as I said, to infer the properties of the black hole, and we have to know which one is happening. Okay. If you ask me, it's probably a combination. This is why it's such a hard problem. But we are trying to constrain this observationally. So this is an event observed. This is work by my graduate student, Sarah Faris. This is the best observed tidal disruption event so far in the optical and ultraviolet. So you have here the light curve from the infrared to the ultraviolet, sampled very well. Each line you see here is a spectrum, so we'll get to that in a second. And what we saw, I was initially thought that the light curves of TDs are very smooth, there's no point in observing them every day, but we did observe every day, and we see that there is some structure in the light curve, there is a change in slope in the rise, there is some bump here at the beginning, and then there were other events showing some bumps in the light curve, and this could be some hint that indeed it's not a single emission mechanism that is smooth, but there are multiple processes going on. So there's still no model that can reproduce this, but we're hoping this will help. In terms of the spectral series that we have, one thing you can measure is the strength of the hydrogen feature with time, and you see it, our event is these black squares. It's the earliest data ever obtained for a tidal disruption event. You see the hydrogen building up, and interestingly, you see this is the offset of the central wavelength of the hydrogen. It gets blue shifted very rapidly at the beginning, and then slowly comes back to the rest wavelength. No model predicted or knows how to reproduce this behavior, and we don't know how common it is because no other events were observed this early. So we're looking for clues for the emission mechanism in this kind of way. And Sarah now found this new event, the first tidal disruption event from Blackton, the survey I showed you at the beginning, which just started. And this one is completely strange, and we have no explanation. You see a first bump at the rise. Maybe this is that nozzle shock I told you about that's dissipating energy. But then for the first time we see here, you don't need a magnifying glass like in the previous one. You actually can very easily see it's a very bumpy light curve on the way down. And this is still, okay. Last week we showed this for the first time at the conference, and no one knew how to explain this. So we'll see what happens. So this is the main puzzle of tidal disruption events we're trying to solve in order to use them to study black holes, but it's not the only one. Perhaps the second biggest puzzle, which is my favorite, is the host galaxies of these events. So this is the phase space of the galaxies where we find these events. On the x-axis, it's H delta absorption. Okay, let's start with the y-axis. This is H alpha emission. This just tells you how much star formation is happening now. So down here, no star formation. Up here, these are star-forming galaxies. The gray dots are all of SDSS galaxies. H delta tells you how much star formation you had a few 100 million years ago. So it's the star formation history. A lot of H delta means you had a lot of star formation in the past. No H delta means you had no star formation in the past. So galaxies typically are star forming now, and then they move down here, and this, you know, that here they are dead and no longer forming stars. But some galaxies go this way, which means in this part of phase space where you have very few galaxies, but almost all TDEs are here. Okay, these points are the tidal disruption events, the first sample at least. These are galaxies that are not forming stars today, but formed a lot of stars a few hundred million years ago. These are known as post-starburst galaxies. Okay, it's like a few percent, maybe 1% of galaxies like this in the field. But all of the TDEs, most of them, except one, which was chosen in a special way, almost all TDEs are here. There's a very high overrepresentation of tidal disruption events in post-starburst galaxies, and we still don't understand why. It's like, depending where you are, so here it's like a factor of 10 overrepresentation, and here it's like a factor of 100 overrepresentation in these types of galaxies, and it's not clear why. There have been many ideas relating to stellar dynamics in galaxy centers, how stars behave if it's a black hole binary, in case these galaxies might be post-mergers. It's actually the dynamicists really started worrying about this problem, how to explain it. So we don't have a solution yet, and I don't have time to talk a lot about it, but if you're interested, you can ask me later. We thought we had a theory, and then this latest model from this year showed it's not possible. So we still don't know why tidal disruption events prefer these galaxies, but this is a puzzle in galactic dynamics and stellar populations in galaxy nuclei. And so this is another puzzle. Why do they prefer these starburst galaxies? But I will not say much more on this. You can say, given all these puzzles, why do you think these are tidal disruption events? Could these be completely different type of transit? So remember that 10 to the 8 solar masses. It's you're not expecting to see a flare around a black hole that's greater than 10 to the 8. And when you count how many tidal disruption events you see per black hole mass, you see this very sharp drop around 10 to the 8. This is a small sample. This has been repeated with a larger sample more recently, and it shows the same thing. The rates of these types of transients show a strong drop above 10 to the 8 solar masses. So we don't know what other type of transient, other than a tidal disruption event, would have this cutoff at around 10 to the 8. Okay, you can get a little bit beyond, depending on the parameters of the star, and depending on the spin of the black hole, you can go a bit higher. But generally, right, this is the black hole population. It should decline much more smoothly, and it's very sharp. This is the main observable that it's telling us these are tidal disruption events, and you need to understand why they emit in the optical and why they like post-starburst galaxies. If that weren't enough puzzles, we found this event, and this is work by Iair Arcavi, who's sitting right there. It was a postdoc at my group until a year ago. This was a tidal disruption event that was very typical. In fact, it was so, at this point we know about, 50 events so far. As I said, it's very rare, and we only discovered this 10 years ago. This was very typical of those 50 events, so much so we didn't know what we wanted to say in the paper, because it was so typical. And then 700 days after it finished, it happened again, in the same galaxy, with almost identical properties. So you're seeing here the two flares on top of each other. Field circles are the first flare, field symbols, empty symbols are the second flare. This is test data of both flares, and you actually can't distinguish them here. You can distinguish a bit in the UV, they're a bit different, but overall it's very similar luminosities, they're not shifted one compared to the other, it's very similar decline rates, and very strikingly similar spectra. The black and blue here are the first and second flare of this event on top of each other, compared to other events. So you see some events have no hydrogen, some have strong hydrogen. This one had exactly this amount of weak hydrogen in both flares. Okay, so in terms of the TDE rates, it's very unlikely to be two unrelated events. They're also very similar spectroscopically, so it's the same event that happened twice. How can this be? Well, the star could not have been destroyed in the first event. It must have been a partial disruption, where the star actually passes slightly outside the tidal radius, but a star is not a uniform sphere. You can disrupt just the envelope and leave some of the star to survive and come back again and get disrupted again. So this is called a partial disruption, right? If you don't fully disrupt the star, you only maybe remove some mass from the star, and then it can survive and pass again, and you remove some mass again. So this has to be, at least the first round, has to be a partial disruption, because it happened again, and it might happen a third time. We'll know in early 2026 if it happens a third time. That will mean the second also had to be a partial disruption. But this is very worrying, because until now all the models and all the solutions to the puzzles assume these were all full disruptions. And now we're saying, well, this one looks so typical Okay, there are two options. Either they are all partial disruptions and all our models are wrong and we have to do everything from the beginning, or partial disruptions and full disruptions look almost identical, which is also a problem, because then it means our class of events is completely mixed and we have no way to tell them apart, okay, or very difficult to tell them apart. So either way, we think this is very important clue. So many interesting puzzles on this field. You can say, okay, even if you don't know any of the solutions to any of these puzzles, you can still use tidal disruption events, for example, to study the immediate environments around the supermassive black hole. Okay, you have some flare of radiation, you don't care why, how, what happened, it's a flare of radiation in the center of the galaxy, it will illuminate the stuff around it, and you can use that to study it. So this is work by Megan Newsom, who's a graduate student in Santa Barbara, who I'm co-advising remotely, who uses the infrared emission. So you see here, this is a tidal disruption event, the flare goes up and down, this is the infrared emission, and it suddenly brightens 2 months after the main peak and goes down. This excess emission above the tidal disruption event itself, we believe, is due to dust echo, or dust reprocessing of the emission, and you can use this to work out the immediate environment around the black hole and what kind of dust it has around it. Another thing you can do is you can use, sometimes this flash of light ionizes the material around it, and you see very high ionization lines. These are known as corona lines, and can go up to iron 14, very high ionization lines that change with time. So we know it's like a response to this flare of radiation from the tidal disruption event. And you can use these to map, actually, the immediate environment around the black hole in terms of its composition. Where you're getting each line. So this is also a completely new front. We can use tidal disruption events to probe the immediate environment around the supermassive black holes. Okay, and this is just the tip of the iceberg of transients around galaxy centers, because once we were, okay, we're looking for more supermassive black hole disruptions, we started finding a completely new class of events. So these are the class I showed you from 2014, that is very broad helium lines. And then we found this new class of flares that when you take a spectrum, you see something very different. You see the same helium-2, but much narrower. And you also see lines indicative of active galactic nuclei. So, and you see these emission lines that come from a mechanism called the Bowen fluorescence mechanism. I won't go into detail, but this was predicted to happen around black holes in the 80s and hasn't been seen until now. You have some cascade of lines that gives you this Bowen flare, and we call them Bowen fluorescent flares, or BFFs for short. So this is even more rare than tidal disruption events, but they are different spectroscopically and their light curves behave differently. They rise and then they decline very, very slowly. So we think these might be related to flares where there was an existing disk around the black hole, like an AGN, where either a star collides with this disk or there's no star at all. It's just some instability in the disk that gives you this flare. And then even more rare, we discovered only one like this, where we saw a flare go up and down. The X-ray went down and up, which was very strange. And the hydrogen lines, this was a no narrow line AGN, and it became a broad line AGN after this flare. We saw the lines broaden. So this is a changing look AGN that we caught while it was changing look. This happened only once. And was accompanied by a flare that doesn't look very different than a tidal disruption event. But we don't know if this is a tidal disruption event or what else, or if all changing look AGN, there are a few hundred now known. But you always get one spectrum now and one spectrum years later, and you see it was narrow and now it's broad, or it was broad and now it's narrow. You never see what happened in between. This was the only one we saw it. So we don't know how representative this is, but we think this is just the tip of the iceberg. There are many transients around supermassive black holes that we are only now starting to reveal. So you say, great, let's find more of them. Turns out this is very hard. This is an undergrad project by a student in my group, Iair Arcavi, now a master's student. If you try to classify every transient in a galaxy center that you find, only 2.2% will be tidal disruption events. Even less of that will be these Bowen fluorescence flares, and everything else is just type 1a supernovae happening in galaxy centers. So it's a real needle in a haystack problem. If you say, okay, tidal disruption events are blue, I will only select the blue events. Okay, you get a factor of 2 improvements, still 4%. You say, okay, tidal disruption events like post-starburst galaxies, I will only look in post-starburst galaxies. Now you're getting quite a majority, but it's very small numbers because we only know of very few post-starburst galaxies. So if you only wait for something to happen in one of them, you're going to be waiting a while. So these things are very hard to find. So if you want to find them, you have to invest a lot of classification time. So this is what we're planning to do with the SOX spectrograph, which is going to be shipped to the NTT in a few months. a brand new spectrograph. It will be completely dedicated to transient science. And the consortium that has built this, that we're a part of, has half the time on this spectrograph for the whole year. The other half, you're all free to propose to use. It's going to be a very sensitive, one-shot, very large wavelength range, like X-Shooter, on this 3.5 meter telescope in ASIA. And looking a bit beyond, we're a part of the Ultrasat mission that's being launched by Israel. This is a UV 200 square degree field of view camera. So it will give you a transient survey in the UV, okay, which you've never done before. And these events, tidal disruption events, are very bright in the UV, so this will immediately distinguish, type 1a supernova is not bright in the UV. This will immediately tell us which ones are tidal disruption events and which ones are not. Okay, so Ultrasat is going to find thousands of tidal disruption events per year. This is going to be really revolutionary. Okay, and that will launch in 2027. Okay, so that's tidal disruption events. Let's move on to core collapse supernovae, which also teach us a lot of complementary physics. And the main puzzle here is what type of stars explode as what type of supernova, or how do stars explode as a supernovae? This is not well understood and not well reproduced by models, and one of the reasons it's a very hard problem. There's a lot of physics that you need to know in order to solve this problem. One thing we can constrain observationally is the progenitor stars, the massive stars that collapse to these explosions. So this is what we're trying to do. The first way you can do it, okay, so the question we're trying to answer is which stars explode as which supernovae. The first thing you can do is just look directly, take a picture of the star before it exploded, hopefully, and then when it explodes, you go back to the archive and you find the star, and you determine what was the star that exploded. Okay, so this is a very common method, except you can only do it in the most nearby galaxies where you happen to have pictures from before. And what people do typically, okay, they take the star from before. What you measure from this picture is the brightness of the star in different bands, if you have them, and then you fit a stellar model to this SED. Okay, and then you say, okay, this is where the star was before it exploded, and you see which stellar track goes through this point. Looks like 13 solar mass star exploded. Okay, and this is what people do. But we wanted to develop a slightly more rigorous approach, which is to say, yeah, okay, but maybe if I take an 11 solar mass star and change the metallicity, or if I take a 15 solar mass star and change the extinction that I assume, I could also get a fit. So what is actually the probability distribution of the mass? So this is a master project by Tomer Katz, who is taking a grid of stellar models and checking the fit to the entire grid, where you can assume different priors and what you think the metallicity is, what you think the dust is, sometimes even the distance is not very well known, and you get a probability distribution instead of one value at the end. This also allows you to check various things like, what is the best combination of filters I need in order to constrain the star that exploded? How does my assumption on the distance of the extinction affect the result? And all of these kinds of things. What wavelengths are the best to use to constrain? So these are things we are now looking at. And here's one example of a star that was studied in a previous case, where the value published there is this line here. But you see now with our method, so we reproduce this value, but we don't get just the value, we get the whole posterior distribution. And you can see how this changes if you assume a different IMF, a different metallicity, a different extinction, and all of that. So you get some kind of better, I think, quantitative assumption. And so he's just finished building this tool and he's looking for a name for it. Okay, so I suggested the progenitator, but he didn't like it. The other student suggested progenit. Anyway, if you have ideas for a name for a tool that finds your star progenitor star, let me know. Okay. So we're going to make this public very soon, and then you can run it on all the cases known and see the distribution. Right now, it's very hard to compare different papers because everyone has slightly different assumptions. The problem with this is that there's only a few dozen supernovae that have had their progenitors imaged. Most supernovae happen in galaxies too far for us to see the star before it exploded. So what do you do there to constrain the progenitor? So one solution is you can find the supernova very early. If you see the explosion very early, the emission from the very early supernova actually remembers what type of star exploded, in that it encodes information about the size of the star, even the inner density profile, and also you can work back the mass loss history of the star right before it exploded by seeing the explosion itself in the very first moments. So this is how it works. So one way is this shock cooling emission. So this is a supernova. You see the main light curve going up and down. But if you catch it early enough, you see this drop. This took just 3 days in this case. And this is the cooling of the ejecta as it expands. The main supernova light curve is powered by the radioactive decay of nickel. This takes a week or so, a few weeks to kick in. Okay, it takes a while to, I should say, diffuse out, and then you see it. But if you catch it early enough, you see the emission source before the nickel decay, which is just the cooling of the expanding envelope. And the larger the star was when it exploded, the less cooling, the longer it will take to cool. Smaller stars will expand very rapidly and they will cool very rapidly. So just from this time scale, you can get the radius of the exploding star. And if you do more sophisticated models, you can actually, this is the density profile of the star before it exploded, calculated from these kinds of data. So you can see this is a log scale, so it had a very compact core of about 10 to the 11 centimeters, and then an extended envelope, which contains only 1% of the mass, up to 10 to the 13 centimeters. This is a peculiar structure for a star to have. We think it's related to the fact that these stars, before they explode, they lose mass to a binary companion, and this explains the stellar structure, but these are the kinds of clues we are getting. Another approach you can do is take a spectrum very early. If you take a spectrum very early, what happens, we saw this for the first time also 10 years ago, you get these very narrow high ionization lines which disappear within hours or days. So what we think is going on here is you have some shell of mass that the star ejected in the years or maybe decade before it exploded, and this is moving out at the escape velocity, and then the supernova happens, and there's about a few hours or a day until the supernova catches up with this material and destroys it. But in that time window, it illuminates this material from the inside. And you can actually see it, and if you see the time in which it is getting destroyed, you can actually work back in reverse what was the mass loss history of the star before it exploded, and that's a really good constraint. This is an example of a model of actually what the star would have looked like before it exploded in terms of the composition. So you can even work out kind of the composition of the star before it exploded and what was its mass loss history before it exploded, which is a really important constraint on models. A third way, third and last, is again looking at the early light curve, but in most stars actually you don't see that shock cooling I showed you before. This is the most common type of explosion where you have a plateau of 100 days in the light curve. It's called the 2P for the plateau. These we believe are explosions of red supergiants, the most common type of massive star. But these are models here where you see the dashed line is what you expect it to look like. And in order to fit the data, which is this solid line, so ignore the blue bands, these are not fit, there's some other physics going on there. But in these redder bands, you see that in order to fit it, you need a solid line here. And the difference between the dashed and the solid line is the solid line assumes there's some additional circumstellar material around the star before it exploded. And again, it slams into this material. It's too quick to see in the spectra, but you see its imprint in the early light curve because it rises very fast. This extra emission is coming. It's shock cooling plus this collision between the ejecta and the material. So this is telling you that these red supergiants, before they explode, have lost some mass, which is quite confined. So it must have been lost quite near the explosion. And this was quite a surprise because they needed to add this to every single type 2P supernova that they tested. So it looked like, do all type 2P supernovas need this, lose this mass before they explode? This complicates a lot the picture that we thought it's simply a red supergiant exploding in a vacuum when it's an easy problem. Right, if it wouldn't have this mass, you would see this slowly rising light curve on a time scale of a week or so, which is exactly what we found. And this is again graduate student Sandos Mohsen found this type 2P supernova that had this very slow rise at the beginning. So our question was, could this be the one that didn't have circumstellar material when it exploded? So you try to fit it with a shock cooling model and it works. So for all these type 2P supernovae, it didn't work because they didn't have this slow rise. Here it works very well. You also tell it, okay, let's try to fit it with circumstellar material. So you try to fit it with circumstellar material and without circumstellar material, and the fit is equally good. In fact, these are again the fit with and without circumstellar material. If you let the model have two more extra parameters, the circumstellar material, which is how much you have and at what radius it cuts off, it actually prefers that it cut off at a radius consistent with 0. So it's like you're telling the model, here have two free parameters, and it says I don't need them. I don't need any CSM, I don't need any circumstellar material. This works just fine if the circumstellar material ends at 0, which is the surface of the star. And so it's really, I've never seen a model where you give it 3 parameters and it tells you I don't need them, okay? And this one says I don't need it. So this is really evidence that this star exploded without any circumstellar material. Why is that important? Before I tell you that, I'll just mention that this fitting code is also something we developed in our group. Here we already have a name, I enforced it, it's called SNEMC. So you fit supernova light curves with a grid of models of progenitors and explosion parameters, and it gives you the parameters of the explosion and the parameters of the star that exploded. So these are very simple simulations, but until now these are numerical simulations. So until now people found one simulation that worked again and said this is the star. Here we do it more systematically and you get the posterior distributions. This was developed by 2 more students in the group. One of them is a biologist who's now doing a postdoc in biology. And Noi, we will meet again soon, is a PhD student. Okay, so why is it important that we have one without circumstellar material? Well, it turns out this one also has, this is temperature over time in a set of supernovae. This one has the lowest temperature of a supernova of this type that we've seen. And this is velocity over time of the ejecta. This one has the highest velocity that we've ever seen. So it's one case. Is this a coincidence that the one without circumstellar material has the highest velocity and the lowest temperature? Or does this mean that when you have the circumstellar material is what's responsible for setting the velocities and the temperatures of all the other class? Okay, so it takes just one rare event to teach you about the whole class of events. So are most type 2p supernovae influenced by circumstellar material interaction, which means do most red supergiants experience significant mass loss before exploding? Because remember I told you we thought that the circumstellar material only influenced the beginning of the light curve. But here there could be a clue that it's influencing the light curve long term, both in the velocities and in the temperatures. So this is telling us that the circumstellar material must be more important than we thought. Again, this is one case, we need to find more and see if this is a coincidence or not. So we want to find more young supernovae. So I already mentioned Ultrasat, big field UV satellite, which we're going to use also to find young supernovae. Blackgem, the telescope I showed you at the beginning, is another transient survey we're involved in together with the Lacia Schmidt Southern Survey, LS4. We're shipping the camera, hopefully this month, down to Chile, and this will be a new transient survey, 20 square degrees in the optical from Chile, and we have waiting for the new spectrograph as well to ship. And in addition, we use the Las Cumbres Global Network of Robotic Telescopes. This is where I did my postdoc, so this is already an existing facility with 22 telescopes, robotic, around the world, ideal for this kind of thing where you need to catch things very early. Okay, so I think I have a few more minutes. I will go very briefly on compact binary coalescence because there have been no events since 2017. So what is there to say about this? Okay, so this was the 2017 kilonova, most probably best observed transient in history, but it showed us it was quite a complex picture. All right, what we thought is happening here, you have 2 merging neutron stars, they eject a lot of neutron-rich material. This material creates our process elements, and these elements are radioactive and they decay and you get a flare of light, except you can't explain it this way. You can't explain the data this way, you need more than one ejecta component to explain it. So the idea is when the 2 neutron stars merge, you have this tidal ejecta that is very neutron-rich and has a lot of heavy elements which are opaque, and so you get a high opacity and this produces red flare. But also in the polar direction you have ejecta that is more electron-rich, and so it's less opaque and it produces a blue flare. And then after they merge, you also have a disk around the merger product which can be irradiated. If this is a neutron star, it will irradiate this disk with neutrinos and you will get blue emission. If it's a black hole, it can't do that and you will get red emission. And if it's a neutron star, so in this one case, in order to fit the data, you need the neutron star to survive for 100 milliseconds and then collapse to a black hole to irradiate the material just enough to explain this blue-red emission. So it's quite amazing what you can do if you can actually separate this light curve into the different components, because the tidal tails are sensitive to the mass ratio, so you can get the mass. This is sensitive to the radius, how deep in the potential well is this coming out, so you can get the neutron star radius, so together you can constrain the equation of state. And this is this is sensitive to the merger products, you can actually tell there had to have been a neutron star for 100 milliseconds before it collapsed to a black hole. But of course, there are alternative explanations to the blue emission coming from a completely different mechanism, also shock cooling similar to supernovae. And in order to tell these apart, we need to observe very early. I had flashed the word cosmology there, so I just devote one slide to this. If you can really tell apart, you can also know the viewing angle, because if you're viewing to the top, you will see more blue emission than if you're viewing from the side. And the viewing angle is one of the biggest uncertainties in using these events to determine the Hubble constant. So as you know, there are two Hubble constant values which don't agree, and this is the probability of the Hubble constant following this one neutron star, which was right in the middle, and is broad enough to encompass both of them. So we need more events, obviously, in order before we can really determine the Hubble constant from this. But the main source of this width is the degeneracy between the distance of this event and the inclination angle. This is determined completely from gravitational waves. So the gravitational wave, okay, the redshift is from the flare and the distance is from the gravitational waves. If you know the viewing angle, you can much better constrain the distance, and then you can much better constrain cosmology. Okay, so I'm going to skip a bit just to tell you we are very bad at finding kilonovae, because there has been one more event since then, which had a very bad localization on the sky, gravitational wave event. And what happened was, all the teams in the world searched this part, which was higher probability, and found nothing. And no one searched this part, which was lower probability, where probably the event was. Okay, so we missed the second ever kilonova, and because we didn't coordinate it, this is another master student project in Ido. I will skip the details, but he showed we could have found the kilonova with the amount of resources devoted within a few hours if we would have coordinated. Whereas in fact, after 5 days, we only covered 50% of the probability, okay, as a community. And this is just models of what it could have looked like, and the bottom line is we could have detected it if we would have coordinated, or we had a good chance. And if not, at least we could have ruled out half of these models. Okay, so coordination is important, but you say, well, these are very competitive groups, they won't want to coordinate, right? They all want to look in the very high probability area. How do we get them to coordinate and find the kilonova better next time? So actually, it turns out that people do want to coordinate, okay? And this is what it looks like if after a gravitational wave event, if you open your email, you get all these lists. People are saying, look, we are looking at these coordinates and we are looking at these coordinates, okay? It's just a complete mess, right? I look at this and there's nothing I can do about it. Okay, so we developed a system called the treasure map, which allows people to report where they are looking in real time in a computer-friendly way. It takes into account the realistic footprints. This is DECA. And it lets you, with basically one line of code, report what you observed and also look where other people are observing. So you can decide in real time, do I want to be the 100th person looking here, or do I want to be the first person looking here? And you can also use this to then see how much area is being searched in time, and it will suggest where you want to look. Okay, so this is the treasure map, and we hope people use it next time there's an event. Okay, the last 2 minutes, if possible, I just want to say, in addition to these three things, there are all these puzzles, and actually the key to solving all of these puzzles is understanding the thing that causes these three phenomena, which is the stars themselves. Okay, so we started realizing we actually don't understand stars at all, especially massive stars. Okay, I don't have to tell you here that stellar evolution for massive stars is far from a solved field, and that we won't understand all of these things, chemical enrichment and supernovae and everything, if we don't understand the massive stars themselves. Okay, just a very simple example. This is a puzzle from 1979, the Humphreys-Davidson limit. This is an HR diagram of one of the Large Magellanic Cloud. Why are there no stars here? We still don't know. Okay, actually, models predict that stars should be here. This is work by former postdoc in my group, Avishai Gilkis, who showed that if you want stars not to be here, one way to get the models to do it is to increase the mixing caused by core overshoot quite a lot, and then if the stars are very well mixed, you can reproduce this limit. Okay, but is that the answer? We don't know what this parameter is in the cores of stars. How do we find out? Okay, so one way to find out is by asteroseismology. This will be the last thing I say. Stars oscillate, and these oscillations are influenced by many properties of the star, including internal mixing. So we want to test do stars really have this high overshoot parameter that causes mixing, and is this the solution? Okay. The problem is this is very hard to do observationally, because the frequency that the stars oscillate are a few cycles per day, but it's in several frequencies that are very close to each other, and then you get big periods on month-long timescales. This is the first study to ever do asteroseismology of a massive star. It was published in 2003. You see they actually measured the core overshoot parameter, and it's not as high as Avishai needs for his models, but this is just one star. Okay, but this took 21 years of observations to obtain, so this is not scalable. Okay, so our idea is let's use this network of telescopes that we use for transients, global network of telescopes, and use it for oscillating stars. If this is the simulation of how the star should oscillate over time, okay, so you see the beat period on timescales of months, you see the different timescales here, why it's so hard, and this is a simulated, if you sample it for 48 consecutive hours, which you can do if you have a global network of telescopes or from space, and you can observe it once a week, you can recreate these results in less than a semester instead of 21 years. This takes 71 weeks to recreate, because the key is you observe for 48 consecutive hours, so you get a much better sampling of the oscillations. You can do it in 17 weeks instead of 21 years. So then you can do many more stars. So this was the idea, and this is Noishi Tait, who's a PhD student now, and she, as a master's, did her proof of concept. Can you use this network to actually do this in practice? The advantages being it's fully robotic and it's completely uniform. The 1 meter telescope here is the same as the 1 meter telescope here. It makes the data processing much easier. So this is real data. You see the oscillations. Each color is a different site around the world. This is 48 hours. This is a little less. You see the oscillations from one side to the other. And this is matching to what we expected the oscillations to be 20 years after that 2003 study. So you see that it works, and it surprisingly fits the expectations quite well, meaning that these oscillations are also very stable over decades time scale, which is something we weren't sure about before. So the plan now is, she got 9,000 hours on this network over 3 years to do 20 stars. This is one of them. We use TESS as well, so TESS is observing these stars and gives you these continuous light curves. Problem is TESS only observes in one band, and for the astroseismic analysis, you need the different colors. So we get the data from TESS and we combine it with data from this network from the ground in the different filters, and the plan is to do 20 stars like this. Until now, only 9 have been ever studied, 9 stars, that's it. We want to triple the sample and do 20 stars. Okay, so hopefully we can get also the parameters of the stars themselves this way. Okay, so I'll just end by saying that I hope I've convinced you that we're still struggling to understand the dynamical universe and how things change in the sky, but that it's really crucial that we do, because we can learn a lot about astrophysics in the way. I've shown you some of the facilities that we've used and some of the tools that we're developing, and these are the people doing all the work. This is took us a week and a half ago when we went to work on some of the telescopes that we were using in Chile. So I hope I managed to convince you that, hopefully we can learn a lot of physics in this way, and I'm happy to answer questions. Thank you.
Thank you very much. Okay, there's time for questions. Anyone want to start?
There were a lot of topics.
I will go back to your first topic and the disruption events, and the fact that you find them systematically on post-starbursts. First question is, well, you're finding TDs from the optical,
yes,
other methods, X-rays, whether similar conclusions can be reached for other selections. Also, other starburst galaxies are kind of special because for example, they also have a high fraction of AGN. And I'm just wondering about the selection effect. Like incidence of black holes in galaxies or mass of the black holes, or whether all that pushes you down in the direction.
Yeah, absolutely. So first of all, I'd say, you see this very strongly when you look at the optical events. When you add also the X-ray events, and most recently we've added infrared events that are seen only in infrared and not in the optical, this changes. So actually, when you add the X-ray events, you still see a preference for post-starburst. It's not as strong, The preference seems to be for green valley galaxies, which post-starbursts are a part of, but this is a broader population. When you add the infrared events, you see them in all types of galaxies. So the question is, okay, so the post-starbursts maybe are just the ones where the dust has settled enough that you can see them in the optical, but actually they happen also earlier in the starburst where they are obscured in the optical. But this doesn't quite work because we don't see any intermediate events. We don't see any intermediate events that are weak in the optical. We either see very clearly in the optical or nothing at all in the optical and everything in the infrared, which is a very strange dichotomy that we don't understand. So some of the ideas were that, okay, so there is still there's some selection effects for sure, but they are not enough to explain the overabundance that we see. So there's some intrinsic effect that is causing them to choose post-starbursts. It could be a Rebic AGN. It could be that what we thought was that post-starbursts have a much sharper density profile at the center, and this could, this could be conductive to more stars being disrupted. But there's a recent work out of the Technion in Israel showing that actually you would get more strong scatterings of the stars between themselves, and you should have less TDs. Okay, so now we also have to overcome this problem. We thought maybe these are post-mergers, and there's a binary black hole in the center, and then one black hole is shooting stars towards the other and increasing rate, but this doesn't work with the numbers either. So yeah, so the short answer is there's some combination of selection effects and intrinsic effect, but even that remaining intrinsic effect, we don't have a good explanation for yet.
Okay, anyone else? Have you considered for the TDs not having a main sequence star, having something evolved?
Yeah, absolutely. So an evolved star could definitely get disrupted at a larger radius, which would then also make the timescales much longer. So you would, instead of these things rise in a few weeks and decline in a few months, you'd have a year-long kind of light year, several years long, and these are actually quite hard to find in transient surveys. Transient surveys, we're always comparing the image today from the image a few weeks ago, and the change is not enough. But people have started finding them archivally in transient surveys, because when you look back, you can say, look, there was a transient here that rose over 3 years and declined over 10 years, and we didn't see it in real time because the difference between two close epochs was never enough, but now we see it, and there's now a class of these. And one of the interpretations is that these are either evolved or also very massive stars that are being disrupted. They are rare, but some of them are incredibly luminous, and with this timescale you get a ridiculous amount of integrated energy. And one way to do it is if you have a massive star being disrupted. But yeah, we're not very good at finding slow transients, but this is one of the science cases where we want to do that for. Yeah.
I have another question.
I was wondering about these events. What is the redshift range that you're probing? Because I'm not in the field.
Yeah. So for tidal disruption events, it's typically less than 0.1. Ultrasat will find them out to higher redshifts, so we can start probing evolution for sure. Okay, there were direct detections of supernova progenitors. This is like 20 megaparsec. You can't go much further than that. But young supernovae, you can go up to also 0.1 maybe, where you can get this good data. The nearer, the better the data, but not much, not cosmological.
One very basic probably question that I don't know if I missed it, but I don't know exactly what is overshooting parameter.
Sorry, you didn't miss it. I didn't explain it.
No,
okay.
Basic,
I'll try not to make a fool of myself here, but massive stars, they have a convective core, or anywhere you have a convective instability in a star, the convection, and then it stops and you have a radiated layer. The convection doesn't just stop, like there's not a strict border. You have some convective cells going over. This is what's called core overshoot. Is what's called overshoot, and this parameter measures in some scale height of the problem how many scale heights it overshoots. So you have you don't have like a sharp edge, you have a convective boundary layer, and how thick this layer is really has an effect on the mixing, and that has a strong effect on the evolution of the star. The more material you mix, you change the lifetime of the star, you change the composition. So you can also get mixing through differential rotation, which is another way, but this convective overshoot, which is how much of a convective cell goes beyond the limit of the convective region, and this influences the mixing and influences the evolution, is parameterized in that now. It's not too wrong, right?
No.
Okay.
Did you have another?
Yeah, I wanted to ask about black gem.
Mm-hmm.
And, well, it's something new.
Yes,
if
black
I'm
gem.
not mistaken.
Yeah.
So I wonder if you could compare it with other similar facilities, ZTF in particular. Or
Yeah. So there are many, for those who are not in the field, there are many surveys now finding transients. The biggest one is called ZTF, it's in California. It has a 48 square degree field of view. This is why it's so effective. In the southern hemisphere, there are actually, black gem is the first, or the first in modern times. This one has a smaller field of view and it's smaller telescopes, but it's 3 different telescopes, so the advantage is you can be much more flexible in the type of survey you do. You can have one telescope doing a fast survey, one doing a slow survey, one doing a multi-band, one doing one color. So we have this combination that allows us to try to maximize efficiency for different science cases. So each, it's like a slightly less than 10 square degrees combined for the 3 telescopes, but you can split it in a much more dynamic way. And because the SIA has such good seeing, you can get the same magnitude depth with that you can. These are 60 centimeter telescopes. You can get the same as you can with the 1 meter telescope. They go down to 21 or 22. So it has been in commissioning. It's already found like 500 transients, including this one weird with the bumps, which I think is really interesting. So yeah, it's not like exceptionally parameter space, but it's slightly novel in the strategy, and it's the first one in the south. LS4 is very similar to PTF, it's just 20 square degrees. ZTF it's just 20 square degrees instead of 40, but otherwise it will be a very similar survey.
Also in the south.
Also in the south, in the same mountain. Actually, we're members of 2 competing surveys, so this will be interesting. And then, of course, we're all waiting for Ruby, which will run the LSST, 10 square degrees down to a depth of 24, but it's not exactly ideal for these science cases, because young supernovae, it will be very hard because the observing cadence, it returns to the same field only after 3 days and in a different filter. So building up the light curves is going to be a bit complicated, and also most of the events will be very hard to follow spectroscopically. So this is our big challenge now, is going to be the classification. So this is why we're hoping SOX can help the new spectrograph. It will be very dedicated. It still won't keep up with Rubin, but at least it will give us a chance.
Great. If there are no more questions, I don't think there are any online. I'm going to check one more time. Any questions online? No, too good. Okay, we can thank Iair here.
Thank you very much.
And hopefully we can go up to the canteen and continue discussions further.
Yeah, happy to.